In this video, we're going to solve the pH of a weak acid solution, both with the simplifying assumptions and by the quadratic. So in this case, let's make a solution that is 0.015 molar ammonium, which has a Ka equal to 5.6 times 10 to the minus 10. Well, our weak acid is going to break apart into H plus and our base, our conjugate base, which is NH3. There's going to be some initial values. Well, we just have a concentration. We can use whatever volume we want. Let's assume it's 1 liter to make our life simple here, so that our molarity is equal to our moles. So we start with 0.015 mole of our starting material and none of our products. There's going to be some change. The only thing that can happen at the moment is that starting material can fall apart. There is no product to go backwards. So we are definitely going to lose some starting material. This is going to create some products, and it's all 1-to-1. Whatever starting acid falls apart, we create exactly that much of our products. Eventually this reaches equilibrium, and so we end up with an equilibrium amount of 0.015 minus x, x, and x. Again, this is all 1 liter, so our molarity is equal to our moles here. Our Ka is going to equal the concentration of our H plus, our base ammonia, over our acid ammonium. Well, for H plus, that's X. For ammonia and H3, that's also X. And for ammonium, that's 0.015 minus X. All that has to equal our 5.6 times 10 to the minus 10. Now, when we believe that X is going to be very tiny, and so that when we subtract it from our starting material, after rounding it will look exactly the same, this simplifies our calculations a lot. We can pretend that this is really just 0.15 on the bottom. So 5.6 times 10 to the minus 10 times 0.015. That tells us that x squared is equal to 8.4 times 10 to the minus 12. Take the square root, and x is 2.898 times 10 to the minus 6. Well, we said x was the concentration of our H plus. So negative log of our H plus is going to be our pH. Negative log of 2.898 times 10 to the minus 6 is 5.5378. We'll keep a few extra sig figs here for a moment. Whenever we have a weak acid solution of just pure weak acid, we can use this method to solve the pH of that solution. Some of the weak acid will fall apart. There will be an equilibrium concentration of H plus formed. We can use the simplifying assumption to make this work easier to solve what that H plus is. However, that's not perfectly accurate. Let's take a look at how good this simplifying assumption is. What if we don't make it? What if we end up with X for our products and 0.015 minus X for our reactant is equal to 5.6 times 10 to the minus 10. And this time, we don't simplify. Well, I'm going to multiply this bottom part up. I'm going to end up with x squared is equal to 5.6 10 to the minus 10 times 0.015. So 8.4 times 10 to the minus 12, but also times negative x. So minus 5.6 times 10 to the minus 10 x. Rearrange this to get it all on one side equal to 0. what we'll find is that x squared plus, so we'll add 5.6 times 10 minus 10 to both sides, plus 5.6 times 10 to the minus 10x, and then we'll subtract the 8.4 to move it over, minus 8.4 times 10 to the minus 12 equals 0. This is the setup for the quadratic equation. X squared, x, and a constant equals 0. Remember, your quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. This lets you solve the possible values for x, one from addition and one from subtraction. A is in front, it's 1. Here's our b, here's our c. Let's do the quadratic. Negative 5.6 times 10 to the minus 10 plus the square root of 5.6 times 10 to the minus 10 squared minus 4 times 1 times negative 8.4 times 10 to the minus 12. Then all that divided by 2. So when we calculate this with the addition, we get 2.898 times 10 to the minus 6. And when we do the subtraction, we get negative 2.898 times 10 to the minus 6. But we can only have a positive value for the x. So the one that came from the addition gave us the positive value. And so our x is 2.989 times 10 to the minus 6. That was our concentration of H+. So the negative log of 2.898 times 10 to the minus 6 will give us our pH, which is 5.5379. Compared to the simplified value of 5.5378. As we can see, there was a tiny difference between the two, but within the sig figs for the problem, we never noticed any difference at all. In fact, well below the sig figs, we never noticed any difference. The simplifying assumption works quite well, simply because we rarely have enough accuracy in our knowledge of exactly what our concentration of the weak acid is to notice the incredibly tiny change caused by X. Weak acids are very bad at being acids. Most of the time, very little of them falls apart. And so the simplifying assumption generally is a far easier route to do these calculations. Situations where you would need to do the quadratic, when your concentration of your weak acid is actually very small. In general, if the molarity of your acid over the Ka is greater than 400 in terms of the ratio, you can make this simplifying assumption. So in our case, 0.015 over 5.6 times 10 to the minus 10. This is a ratio of 2.7 times 10 to the 7. This is 27 million times the difference. Well outside the range where we'd have to be concerned that the X might become too great and actually affect our calculation. So as long as your acid concentration versus its Ka in your solutions of just weak acid is more than 400 times greater, the simplifying assumption can be made.